자, 수업을 okay. Well, today is December 12th. We will start the class. 그 컴퓨터 세팅이 좀 잘못돼서 아직도 문제를 못 풀고 있는데 그냥 태블릿 없이 하도록 하겠습니다. 잘 들리죠? 자, 윈도우 태블릿이 안 돼서 윈도우 프로그램 인스톨레이션 프로블럼인 줄 알았는데 그게 아니라 지금 그 태블릿의 하드웨어적인 문제인 것 같아요. 태블릿 없이 시작하도록 하겠습니다. Okay, well, today is December 12, 2020. This class will be our last class this semester. Well, we hope to finish programming our tool, which is called high CLT, classical laminate theory, based on micromechanics. While we are reviewing the failure criterion, one of them was Zayu, which is based on the quadratic criterion. In other words, the failure criterion, dependency on the stress is the up to a second order. This is a linear term, and this is a second order term. That's why it is called quadratic failure criterion. And now we have a constant Fij and Fi who are determined based on the strengths, and we define the strength ratio, and using the strength ratio we can easily judge how safe the structure is for the given stress field. And another very famous failure criterion is the Hashin. I'm sure you went through this criterion and tried to develop a tool based on this criterion. I reviewed them, but not much satisfactory. So it is important to understand not only Zayu, but also Hashin failure criterion, because when we design structures, especially the composite structures, the failure criterion will give us a guideline, meaning it gives us how safe the structure is. Design means that how many layers we need to have, what kind of angle distribution we should have for the given the load. So it is extremely important to to understand the failure criterion. Well, I just typed in Google search, I just typed the Hanyang failure criterion and try to show you how well this failure criterion is being used in industry. Well, this Hanyang is implemented into most of our CA tools, Abacus and ANSYS and etc. So Hanyang, again, we need to understand. For example, there are several Hanyang modifications, but fundamental idea is the same. This is several papers based on the Hanyang. Basically, what we share the failure criteria. That's the one, the very important. We do have okay, I will go through the equations. This is the one. Now, it is important to understand the failure mode. Well, failure mode means we have 4 different failure mode. One is the fiber tensile failure. The composite will fail. Composite will fail, say, in case the fiber failed under tension. So that is the most dangerous failure mode, which we have to avoid. So fiber failure mode, let's say the fiber is along these directions, one direction, or we are using the X coordinate, so X directions, and this stress along this fiber will break the fibers. So this is the fiber failure mode for tension. See here, subscript, we have a T. So it's a tension mode. And simply the fiber tensile failure will occur when in the combination of a sigma 1,1, not just a sigma 1,1, but also a sigma 1,2. Sigma 1,2 means that shear mode, the well, shear does not show here, but the sigma 1,2 is the longitudinal in-plane shear stress and divided by the shear strength. So it's a quadratic form of the sigma 1,1 and sigma 1,2. So this is the fiber tension mode. So sigma 1,2 is like this shear, along this shear. So this is the one this way and this way and this way. Okay, so this is the sigma 1,2, and when sigma 1,2 reach its strength, the fiber will fail as well. So that's why in Hanyang we have the fiber tension mode is depending on not only fiber direction, but also in-plane shear. Okay, well, that's why we have these terms. And fiber compression is when the stress along the fiber is negative on the compression, the fiber will fail. It's called fiber compression failure. And we have a index, okay, this D, is similar to R, strength ratio, but the physical meaning is different. And D is just index. And D scale equal, this is just a definitions. And matrix failure. And matrix failure means it's like transverse load. Transverse load, the symbol is different from what we are using. So this is actually sigma y. When sigma y is a positive, then the failure mode will occur like this. And also not only sigma to y, but also sigma s, sigma longitudinal shear. That in-plane shear occur not only here, but also here, right? So this is the matrix tensile mode. And matrix compression mode, this is a little complicated, but as you can see, sigma 2,2. When sigma 2,2 is a negative, the failure mode will depend on the sigma 2,2 and the sigma 2,2 here, but the sigma YC is compressive strength. Okay, the compressive strength here. Compressive strength. And the ST, okay, ST is the not in plane, but out of a plane mode strength, and YC is the compressions. The ST here, okay, ST here, and the YC here. This is the compressive transverse strength and sigma 2,2. And ST, again, ST is like this one, out of plane shear strengths. And again, there are little different versions and modifications. And so let's try to program. Okay, let's try to program. Well, oops. Here is the another expressions, Hashins. You can find them in this in the reference. While there are a little, as you can see, there are little different little modifications. There is another factor. It's called a beta. But anyhow. So let's try to program this, but very importantly, we need to define the strength ratio like parameters, okay? D when D, we can calculate this D, and when D reach one value, one, then it will fail. But what we like to do is we like to define the strength ratio like parameters. So as we did in the Zayu, this definition is critical. So let's say we have a sigma, which is the applied stress, and the divide by the allowable strength, allowable stress, and the ratio is the R bar. And so instead of this sigma, we define the we can define the R bar. Well, it's very difficult without writing. So well, so again, the sigma 1 and sigma 1, 2 is the stress we calculate from on axis. Now we like to define the R bar, which is a strength ratio. And how do we define R bar? Well, failure occurs when D equal to 1, okay? D equal to 1. And this applied stress will be replaced by the R bar times allowable stress. So that will be inserted here instead of sigma. As you can see here, the R bar is defined by the stress applied and the stress allowed. So when we have a stress equal, for example, 2, twice, then this allowable, say 1, and the stress applied is a 2, then the R bar will be simply 2. That's what we like to have. That's what we like to define the R bar. Again, the allowable stress is when allowable stress equal 1 and applied stress is bigger than 1 with a certain ratio, say 2, then R bar will be 2. That's what we like. If sigma apply is less than 1, for example, 0.5, then R bar will be 0.5. So say this is the allowable. Allowable means that this one will substitute into here, then this will be 1. 1 means the failure occur. Okay, so sigma, this allowable will be put it here. In other words, sigma, sigma apply divide by R will be put it here. Okay. Need to just 1 second, please. Okay.
Say,
I'm gonna
I like to share. Understand.
Well, I'm
But I'm
not
not prepared for this class without. Let's see. New screen.
Just
1 second, please. Okay.
Well, I hope it works. So what I'm doing now, I log into device and I'm using iPad to type in. I hope you see what I write. so sigma 1 divided by xt and square, this is a square, plus sigma 1, 2, and SL and square. So certainly D, when D equal greater than 1 and equal 1 and less than 1 and greater than 1 will certainly will say unsafe. But we cannot tell how much unsafe. That's my point. And it is not proportional. So as I mentioned, we define a sigma allowable. Allowable means that this term will equal 1. Okay? Because when D equal 1, the moisture will fail under this stress. So when sigma allowable, when allowable and D equal 1. Now the point is that this allowable will be replaced, say R and sigma. Sigma is a real applied the own axis stance. Okay. So let's put it here. And 1 equal and sigma divided by R. Sigma 1 and say xt and square plus and sigma 1 2 divided by again R and XL and square. So as you can see, and simply R square equal sigma 1 1 and xt square plus sigma 1 2 XL and square. Well, it looks like this one and here R and D is originally defined. It looks the same. Yes, it's the same. But when we have a different failure mode, this R and D would have a different meaning. So anyhow, this is the equations, and so R will be square root of this square plus and this. Okay. Let's try to. This is the one failure strength ratio. I will call since this is the say fiber tension, so I will call fiber tension. And another one is the fiber compression. Okay, I'll write down here as a fiber tension and all fiber tension. Now another one, the second one will be a fiber compression. When sigma 1 is a negative. So this D fiber compression scale is simply sigma 11 divided by the XC and scale. So if we do a same procedure as before, then we can simply say the R fiber compression will be simply a absolute sigma 11 divided by the XC. You may wonder again, what's the difference between D and R? Well, if this is the old, this is the A definitions of the alba. Okay, very important. So this is the A proportional, and it's like the safety factor which we define in the XIU. But this D does not have that physical meaning. Well, in this case, it happens to be same as the alba. But if there is a scale term and if there is a linear term, then the meaning will be quite different. So we have to go through. We have to define this kind of definitions. And third one will be a matrix. A matrix tensile failure. And the matrix tension equal again this is a scale as well, sigma 2 and YT and scale plus sigma 1 2 and XL. And since this is the also same as the fiber tension, we have a scale term. So if we go through the same procedure as we did, then R matrix tension will be the same as the sigma 2 and YT and scale and sigma 1 2 and X L. Okay. So this is the matrix tensile failure. And matrix compressions. Matrix compression. This is the important sigma 2 less than 0, and this is a sigma 2 greater than 0. And the matrix compression was defined as scale and sigma 2 and 2i's of ST and scale plus and YC and twice of ST. And you may wonder how these equations are derived. Well, we can refer to our original paper published by, authored by the Hashin, which was more than 30 years ago. We can refer to that one. But anyhow, we just accept these equations. So now, okay, this is the Y expression. Well, this is the what we have in our lecture note. And now here again, we submit as before. And this is gonna be 1, right? When fail, DMC equal 1. And now here, the R scale and sigma 2 y sub ST. And again here we use as before, and this is the one we are using. Okay, sigma allowable. Sigma allowable equal define the real stress and alpha. Again, allowable means that t equal 1. Okay, so this one will be like that, and here and yc divided by 2 st square plus minus 1. This is the AA constant. Doesn't need to be changed. But this one, there will be a 1 over r. And sigma 2 divided by yc. Right? And now, this is the second order equation we have to solve. So r square and sigma 2 to y sub st and square plus and r. We multiply r square in both terms, and r and yc twice of s st and square minus 1 and okay and y, the sigma 2 and yc. Okay, well, as you can see, this is the second order equations. Everything is clear, and here and here is this and here. But here we need to solve the second order equations, right? So we I will put it in the order. Equal 1 equal 0, and this going to be minus and minus. And this is the well, these terms and this term we usually say AR square plus BR plus C equals 0. This is the second order equations. And R will be simply minus B plus we don't need a minus here. B square minus 4 AST. Right? So we're gonna I'm using these equations and A equal 1. So R will be A equal 1 simply. So half. And now minus B, actually this is the AB. We have a minus here, and this is B. So minus B will be simply YC by EST and square minus 1 and sigma 2 and YC. Right? There's a minus, but there is also a minus as well. Okay, so this is the minus B and plus root. Well, I will just call this one. Okay, I will just call this one here, and then this is a square minus and A equal 1 and
C.
C
C is here.
So
So this is going to be a plus and 4 times. And sigma 2 twice ft and square. Okay.
Well, please pay attention to the term here. We have
sigma 2 here
and
sigma 2 here. Right?
Okay. Let's see. Let's get back to our original one.
And I think something is not quite. Minus b plus b squared plus 4ac. Okay. And then we need to parentheses here.
Okay. Well, then let's program these terms. Okay, we will program this. By the way, this one we need to call matrix compression. So what you're going to do is that we calculate the fiber tension and fiber compression and matrix tension and last and matrix compression. So we're going to calculate all these terms and also R. By the way, I omit and bar here. Okay. And R, I will say Hanyang will be a maximum of these. All of these. And that's the one we can judge. But it's better to plot all of them, meaning 1, 2, 3, 4. These 4 strength ratio and also this one final strength ratio. And then we can see which value can be a major one controlling failure index. Okay, so let's program this one. Well, it is 3 o'clock right now. We're going to have a 10-minute break and we will come back. Okay? Thank you. So we are programming this 4 different failure modes. Okay. Actually, last time the R bar and R bar T1 was based on the SIU, and this is the based on the epsilon X failure. It's like netting theory. Now we are using the Hanyang. And I would say I will call I'll add key. Okay. And let's call R fiber compression and R matrix tension and R matrix compressions. And then finally we're going to define the R hashing. And R fiber tension is sigma 1, so simply like a scale root. And sigma 1. Now what is a sigma 1? Well, sigma 1, as you can see here, we have our own axis stress. Stress and X and K and Y and S at different positions. Okay, so it's better to have STR and X and K. No, we are following this equation. Okay, we need to have this and square and plus and stress a shear and K and divide by well, I will divide by strength. Okay, we need to divide by the X and the tension, right? Extension. And here we need to divide by the S, and we define the SS, right? And the square and square root. Okay, that's the one we have. And now, but we need to define a different position, meaning the top and bottom of the prime. So this we call K, and all of this one will have a name as K. And of course, it's important to have a define the variable name in programming. And here we're going to have K1. In naming, we have to have a consistent naming, which is very important in programming. And this is going to be 1. Okay. Now here, fiber compression. Where is the fiber compression? Well, fiber compression is here. And so this is the called absolute stress and X and K divided by X and compression of prime and right. Okay. And another one. Oh, by the way, we forgot. And this one, RFT, is the if stress X, K, when positive, right? Positive and positive and equal 0. Then this. While we can have a one just okay, let's combine these two. Okay, combining means that here this is when this is the negative. So we're gonna have this one. Say if this is a positive, and the failure strength ratio will have the this term, and if not, then this will be the equation. So let's update. And then we don't need to have a fiber tension, and just the RF fiber. Okay, I will just say fiber is better that way. We don't need to define the compression. And let's say this is the R matrix. Okay. And we don't need to have a compression. Okay. And we don't need this. Okay, good. Now the matrix tension and matrix compression. Let's do that. We're gonna just copy these equations, and then when matrix Y is a positive, we're gonna use this one. So this is the Y, and divide by YT. So divide by the YT, and also in the second term we have a sigma 1 to shear and S square, right? And now matrix compressions, and which will be a half 1 over 2 multiplied by the but we are typing this equation, okay? And here and okay, so y prime divide by 2 divide by S. Okay. Well, this is not the SS. This is the SL, and this is ST. We didn't define the ST yet, which we will do that. But anyhow, here and the minus, we are typing this, and we here we have a square, and we can delete this, and then minus 1, right? This one, and then type, I mean differences, and multiply by the stress and K, a Y and K divide by Y compression. We define the YP and like that, right? Have this and that. Okay. And plus and square root of this term. And this term is from all the way here to there. Right? And plus 4 times, and the stress and Y and K and divide by 2. 2 divided by the s t, which we will define. Okay. And then square and square root and parentheses. Okay. Let's double check the applications. Okay, so when this is the positive square root, this and that, okay, which is fine, and for instance this here, this term, can I see color well? Plus and here and plus here, and we need another parenthesis. Oops. Oh. Oh. If positive. Okay, what is we need to parentheses here, and then what? 1, 2, 3. We don't need one of these. Sorry. Square root. And this and that and here. And square. And this. I cannot see the color. Well, I'm gonna this is not type of formula. What does it mean? When the first character is unequal, 1 minus sign, exerting is a formula. What's wrong with this? Okay, well, I'm gonna try this. I'm gonna type this one. Okay. So this is the first term. Okay. And we have a second terms. and second term. What I like to do is the has a two terms, one positive and negative, and this one square root, and this square. We need. Sorry, what's wrong with it? All right. We need one more parenthesis. It should be okay. I don't know. I don't understand. Pause. Okay, so instead of that, we will have that terms for this. We'll have a and when positive. I'm sorry it took so long, but again, this term I just separate. And so this term will be this term, which we don't have to define the name. And this term we have here. So it's a little simpler. And so this is gonna be like that, and this is gonna be like that. This is a temporary variable, and now our matrix is defined like that. Okay, and we don't need to have these terms. Okay, so now we finally define this. Okay, we have we're gonna have a name for this. Well, up to here, have a name. Oops. Okay, and then Hashin at K equal a maximum of R fiber K and R matrix K. I don't like these terms. Okay. Now, I will just copy all terms and paste it here. And then all the stress with the K will be replaced by the K1. Okay. So select them all. And the K will be replaced by the K1. Right. And then we will define the name. Okay. Now finally, we can define this one is the Hanyang at K and Hanyang at K plus K1. Okay, well, that is the I think is enough. And then let's see. Let's plot them. Let's try to plot them. And as you can see here, we have this Hanyang value at each term. So what we like to do is that we need to have another maximum at K among all these phi. So I will call R max. I will say Hanyang max at K, and this is gonna be a maximum of the R max at K. Right? Again, the max. This is the R Hanyang K. R Hanyang K. Same for this, call K1, and here will be K1. And we will have a name. Oops. And the name. Okay. Well, so I will have a color for this, and we'll have a color for that. And then let's say you can define the R, say R Hanyang at K. I would say we have a maximum Hanyang K. Actually, we can have a maximum of this maximum. Max. minus Hashin and K1. Oh, we have another max here. Sorry. So many maximum here, but that's what we need to have. See, first maximum is the amount pi, and this one, and maximum of this K and K1. So I will say this is the R. I will just say Hashin. Now this one, first one was the R max. Actually, this one was the Zayu. At that time, we didn't have a Zayu name there, but anyhow, we have a. I'm going to change the format. And something like that. And take a look at these two values, and looks very similar. And we need to first we need to plot them. We like to plot them. This is the alpha K. Alpha K is the at K, and we can also say I will just call Hashin at K, and this is the a plot along the ply, and we define this name at the K. Okay, at the K we call R Hashin K, right? R Hashin K along the ply. So R Hashin K, this one. Okay. And then we just copy and plot here. Okay. So let's try to plot this. Okay. Plot this z coordinate, and also this is the Zayu and Hashin. Let's plot them and see the difference. Okay, see the difference. Now, this observation is very critical. As you can see, this value is first of all very uniform. Why? Because let's take a look at this layup sequence. Layup sequence and load. And as you can see, this is the just plus minus angle pi. As you can see, in this case, 90 and minus 90 and so on. And the value, graph-wise, the value look different, but the value-wise is not that much different. Like to change the minimum, it's always a zero. And as you can see how small it is, the difference is very small between the psi U and Hashin. And so like to compare Hashin and Zayu for different. See, this one is the again. I would like to remind you that the case. This is the pressure vessel light load N1 versus N2, and this is the symmetric and plus minus theta. Angle pi laminate, and this is the angle as a variable, right? Okay. So let's pressure vessel and like Hashin, and we can change the angle from 0 to 90. And see, plot this difference. Okay. So this is the result, but importantly, very similar between the Zayu and Hashin. Okay, but the Hashin gives us the physical meaning, whereas the Zayu does not have any physical meaning, just one index. So we have a pros and cons. So what we like to do is we like to plot this fiber mode and matrix mode. Okay. In matrix mode, we just have a matrix and fiber, and matrix fiber and different K. That's the so easy, very easy to add them. Very easy to add them. So here we can have a say we just plot at K. Okay. We can plot K1, but just plot K, and here we can have Hashin, we can have a fiber, right? And also fiber K. And another one is what? While we have a matrix. we have a matrix. Okay. Okay. So we copy. Oops, what is that? I don't understand why I keep this. Matrix NK. And then we copy from here to there. You can, first of all, you can plot these values along the pi, and here see, you remember the maximum of this R Hashim K, and maximum I will do this way. Here I like to add two more variables. One is the Hashim matrix. Oops. Matrix, and this is the fiber, and this is gonna be a maximum. Why so many maximum? And Hashim, Al-Hashim, this is gonna be a fiber, right? Fiber. Okay, so fiber at K and maximum. That is the one means. I'm sorry, this is gonna be a maximum. You have the fiber first, and then it's gonna be a matrix. Okay. Again, I like to summarize. This is the fiber, Hashim fiber for all price, and this is the matrix fiber matrix for all price, and then this one is the maximum of everything. And let's try to plot again. And in addition to this, we have two more, as we just defined. We have two more. One is the maximum, the fiber, and matrix. Let's see how it looks like. Okay, this. Now, I'm going to get rid of the Zayu. And Zayu. This is the one is this one. Okay, I'm going to delete this. Okay. This one shows the variation of a Hashim, very important observations. And while this one see, along this angle from 0 to 90 degree, this is the strength ratio, And for matrix mode and fiber mode. And you can see how it values are changing. And compared to this is the maximum of the fiber resin. And as you can see, the fiber mode is not so important, and fiber matrix failure mode is critical, as you can see, all the angle, along all this angle. And that's why we have as you can see, we have a Hanyang, maximum of the fiber resin, and importantly, this gives us a physical meaning. And this matrix failure mode is the one critical for Hanyang. And which is very similar to SIO failure. I mean, this is not always the case. This is the case for this typical loading case and layup sequence. And again, very importantly, the SIO does not give us any failure mode, but the Hanyang give us the failure mode. In our case, the Hanyang failure mode is late or controlled by the matrix failure. Okay? Why? Because the fiber mode matrix. Okay. So this is actually what I like to cover today. Very sorry it took so long because my tablet didn't work. I don't know why, but I need to replace it. Okay. Actually this is the end of a whole class. I mean, this semester. We wanted to cover the strength analysis, which we did for SIO and Hanyang, mainly. Very important again. But fortunately, there is something I like to cover. That is basically a programming of this polling, but that is not so important. Okay. So we would like to, speaking of the final exam, that is very important for you. And I would like to announce it through cutoff. And mainly it's gonna be, we're not gonna have a in-class exam because of any reason. Instead, I would like to assign a term project, and which will be due in 1 week. Sure, it will take several days, so you better start early, which I will assign today. Through cutoff. Okay. Again, sorry for delay. But all the derivation has been recorded, by the way, as usual. You can always watch the video for getting back to a little details. Okay. If any question, and please share your question through Hato. And this is the again end of our class. This is semester. Thank you so much for following class. And we didn't have a chance to see each other. But we will be in contact. Again, if you do have any questions regarding research on the composite material design and analysis, feel free to contact me, and I will be happy to share my idea or directions. Okay. Well, again, it's not the end of learning about the composites, and there are a lot more subjects we need to cover. I was trying to relate to micromechanics, fiber and resin, and macro, which is very important, not just for the stress analysis and failure analysis, but also for fatigue analysis and impact analysis, many other. So you can, I hope you can, able to extend to cover all different types of analysis. Okay. Again, thank you so much, and wish you very good luck for even these corona pandemic situations. And soon, nevertheless, we will have a wonderful holiday and Christmas and year end, New Year. Well, this season is not going to be as pleasant as before, but well, you can have a different type of holiday. I hope. Okay. Thank you, and take good care of you and your family. Bye.